All right, welcome back everybody. In this video we're going to talk about material from section 9.6 of AP Calculus BC, solving motion problems using parametric and vector valued functions. All right, a little bit of an introduction here. So when a particle moves through the plane, if we think about the motion in terms of the parametric functions x equals f of t and y equals g of t, we can imagine this, this particle or whatever object moving all around in the plane as time passes by. The points f of t, g of t make up a curve that describes the particle's path, and that path could look, like all kinds of things, traveling around in the plane. The vector r of t, which is f of t, g of t, from the origin to the particle's position, is what's known as our position vector. Okay, so now let's apply what we know about vector-valued functions to motion problems. What we know about vector-valued functions and parametric functions. All right, so first a few bits of definition here for us. Given a position vector r of t with x of t and y of t as its components, the following motion relationships exist. The velocity vector is just the derivative of the position vector, which we get by taking the derivatives of the components of the position vector. The acceleration vector is just the derivative of the velocity vector, which we get by taking the derivative of the components of the velocity vector, or second derivative of the components of the position vector. And then speed, which is the magnitude of velocity, all we're going to do is find the magnitude of the velocity vector, which we're going to find by taking the square root of the components of the velocity vectors individually squared. All right, so let's look at our first example here where we'll find some of these pieces of information. Example 1, we've got position vector r of t equals 4 cosine t and square root of 2 sine of t. It's the position vector of a particle in the plane at time t. All right, first thing to find, the velocity at time pi over 4. So first we're going to find our velocity vector function, v of t, by just taking the derivatives of the components, and so that's going to be negative 4 sine of t, and the square root of 2 cosine of t is the vector, the velocity vector. Now we want the velocity at time pi over 4, so we're going to take this velocity vector and substitute pi over 4 in there, and so that's going to be negative 4 times the sine of pi over 4. Sine of pi over 4 is root 2 over 2. So negative 4 times root 2 over 2 ends up being negative 2 square roots of 2. And the square root of 2 times the cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. So we've got square root of 2 times square root of 2 over 2, which is just 2 over 2, or 1. And there is the velocity vector at time pi over 4. All right, the acceleration vector at time pi over 4, we're going to go ahead. Acceleration is the derivative of the velocity vector. So we're going to take the derivative of this by components. So the first component of the acceleration vector is going to be negative 4 cosine of t. And the second component, the derivative of this, is negative square root of 2 times the sine of t. And there's our acceleration vector, which now we're going to find the value of the acceleration vector at pi over 4. So we're going to go ahead and put pi over 4 in here. The cosine of pi over 4 is square root of 2 over 2. So once again, my first component of my vector is going to be negative 2 square root of 2. And then the second one, negative root 2 times the sine of pi over 4. Sine of pi over 4 is square root of 2 over 2. So this is negative 1. There's our acceleration vector at pi over 4. And then lastly, the speed at time pi over 4. Speed is the magnitude of the velocity vector. And we already found the velocity vector at time pi over 4. So to get the speed, remember when we were doing, motion along a line, we just took the absolute value of the velocity to get the speed. Here we're taking the magnitude, since we're going in 2 dimensions, and the magnitude of the velocity ends up being our speed. And so this is going to be the square root of the first component of the velocity vector. Well, we already did this at pi over 4. Let me erase that and say, hey, I'm going to find the speed at pi over 4. And that's going to be the x component of the velocity vector squared plus the y component of the velocity vector squared. And so I square these out. Negative 2 root 2 squared is 8, and 1 squared is 1. And so the speed at pi over 4 is going to be 3. All right, that takes us to the end of our first page. On to our second page, a few more motion characteristics that are all related to one another. Displacement, position, and total distance traveled are concepts that we've talked about being associated with one another in rectangular coordinates, and similarly they are associated with one another in vector value functions and parametric functions. The displacement from time A to time B, just like the displacement in rectangular coordinates, the displacement is the integral of the velocity. And so now we're integrating the vector-valued velocity function here, which we do by integrating each one of the components of the velocity function individually to get the displacement vector. The position at time B, when the position at time A is known. So position at time B, there's my position vector at B, is equal to my position vector at A, plus the integral from time A to time B of my velocity vector. This is just like when we did it for Cartesian coordinates, the position at time B. When I knew the position at time A, I took the position at B, and that was equal to the position at A plus the integral from A to B of the velocity. And here's how I would calculate that. I would take the initial position vector and add to it that integral vector of the velocity. And then total distance traveled. Well, if you remember when we did total distance traveled in rectangular coordinates, initially it was hard for us because we had to figure out when the velocity was positive and when it was negative and where it changed directions and compensate and all that kind of stuff. And then we learned about integrals, and we could find the total distance traveled by integrating the speed function. Same thing for vector motion. In order to find the total distance traveled, we're going to integrate the speed. And the speed for a vector-valued function is the magnitude of the velocity function. So we're taking that formula that we just used on the previous page to calculate the speed, and we're integrating it from one end of the region to the other. All right, let's look at example 2. The velocity vector of a particle moving in the plane is dr dt equals 2t, 1 over t plus 1. Part A. Find the particle's displacement from t equals 0 to t equals 4. So the particle's displacement is just going to be the integral of the position function. And so we are going to integrate that from 0 to 4. So this is going to be the integral from 0 to 4 of 2t dt, and the integral from 0 to 4 of 1 over t plus 1. That's equal to, let's see, the antiderivative is t squared, and the antiderivative is natural log of the absolute value of t plus 1. 0 to 4, okay. Oops, forgot to evaluate this from 0 to 4 before I put those braces on there. All right, and so this integral ends up being 16, and this one ends up being natural log of 5 minus natural log of 1. Natural log of 1 is 0, so the component ends up just being natural log of 5. There's the particle's displacement. It's that vector. It moved 16 units in the x direction in the plane and natural log of 5 units in the y direction in the plane. Part B, find the particle's position as a vector function of t if r equals the vector 3 natural log of 2 when t is equal to 1. All right, so my position vector is going to be the integral of my velocity vector. So this is going to be t squared plus c sub 1 and natural log of the absolute value of t plus 1 plus c sub 2. And then I'm going to find my constants. This should be 3 when t is 1. So 1 squared plus c sub 1 is equal to 3. Means that c sub 1 is equal to 2. And this is supposed to be natural log of 2 when c is equal to 1. So natural log of 1 plus 1 plus c sub 2 is equal to natural log of 2. And therefore c sub 2 is 0. And so my vector function is going to be t squared plus 2, comma natural log of the absolute value of t plus 1. All right. And then I could use that to find the position of the particle anywhere that I wanted to, like time 5, for instance. And then, lastly, find the distance the particle travels from t equals 0 to t equals 2. Okay, so I'm going to go ahead and integrate the speed from 0 to 2. The speed function, speed is the magnitude of the velocity, so we're going to use the components of the velocity inside this radical. And there's our setup. Oops. Don't mind me. I never learned to read. That should be 1 over t plus 1. And most of the time when we're doing these vector functions, say on our AP exam, we're going to have our calculator to help us. So I'm going to go ahead and we'll take the integral of the square root of the quantity 2t, quantity squared, plus the quantity 1 over the quantity t plus 1, quantity squared, close the square root with respect to t from 0 to 2. I think I should have, let me click this button first. There we go. And we'll let this thing calculate the distance that the particle travels. It takes a little bit of time sometimes for it to calculate stuff like this. Hopefully not too long. I'm running out of time on this video. There we go. 4.335 for the distance that the particle travels. All right, that's where we're going to stop for this video. We will come back and do a shorter video for the second part of this lesson. All we're going to do in that video is we're going to actually work through a calculator free response question from the AP Calculus BC exam from a few years back. I guess it's more than a few years back now. From some years back, we're going to go through an AP free response problem and incorporating all of these concepts of, solving motion problems. Okay, until then, have a great rest of your day, and we'll see you then. Bye-bye.